after the second talk this morning. And we'll meet in front of the room, and Eduardo will lead us to the roof of the building. And second, if you are picking up a check or cashing a check, please bring your identification, either passport or other identification that's needed. And third, if you haven't done so, please sign up for the dinner, or actually lunch tomorrow. The conference dinner will be a lunch tomorrow in a churrascaria. And I hope you can come, as many as possible of you can come, but we need a head count. So please go to 208, the business office, and sign up by the end of the day. Thank you. So our first speaker of the morning is Claudia Polini from the University of Notre Dame, and she'll talk about Rie's algebras and singularities.
So first, I would like to thank very much the organizers to have given me the opportunity to come here and to speak at this beautiful conference in honor of Steve Kleiman and Aaron Simes. It's a pleasure to be here. First of all, I love Brazil, I love Rio, so it's a pleasure to be here. And second, it's a pleasure to honor these two brilliant mathematicians. I know Aaron since many, many years. You know, I was a student at Rutgers of Volmer Vasconcelos, and Volmer and Aaron are best friends. So Aaron visited Rutgers many times while I was a student, and we got to know each other. I got to be influenced by his way to do mathematics and also his way to mix geometry together with algebra, and we became friends. And I must say that the things, I want to be short, I maybe talk more about it at the conference dinner, but I would like just to say that for me, Aaron is an inspiration mathematically, but is also a deep friend and somebody that has supported me during my career. I felt very much that Aaron always encouraged me, helped me, and also was always close to me mathematically and professionally and from the personal point of view. So thank you very much, Aaron. Congratulations for your birthday. I also want to say one word about Steve. I met Steve. I knew Steve mathematically much, much longer, and I read a paper, I remember in 95, a beautiful paper that he wrote with Ulrich. And you know, I knew him mathematically, but not personally until 2000 in a conference at Lumini. And when I met him, I was completely, he was so nice. So, I had this, this big mathematician. I meet him. I thought, I'll be intimidated. He made me feel at ease, and he was very encouraging again. And I felt very supported also from him. So I'm very happy to be here and speak at this conference. Thank you very much. So I'll start talking about Rie's algebra and singularity of rational curves. This is work that is inspired by work of Aaron all his life, as Byrne pointed out. So we talk about rational plane curves. C is our curve. We assume that C has degree D, so it can be obtained, is parameterized by three forms. Let's call them F1, F2, and F3, and they are form of degree D in a polynomial ring in two variables, X and Y. Without loss of generality, we can assume that this is actually a map, is a regular map, and also that the degree of the curve is D equal to the degree of the free forms. And we consider the ideal I. We assume always that K is algebraically closed through the whole talk. And we consider the ideal I, I'm a commutative algebraist, so generated by the free form F1, F2, F3 inside the polynomial ring R. It's because C is a regular map, we immediately get that the codimension of I is 2. And we want to study the singularity of this rational plane curve. And the point is, one could ask, this is a classical subject. There are tons of books and articles wrote about it. What is else to do? Actually, there are lots of open questions in the subject. For example, if you look at cuspidal curves, it's an open question how many cusps can be. Theoretically, we know the bound is 8, but all the examples have much less cusps. So the other point is we want to look at this from the commutative algebra's point of view. So we want to study the singularity of the curve using the CZG matrix, using the matrix of relation on F1, F2, F3 on the ideal I. So we have the Hilbert-Birch matrix of I, is a 3 by 2 matrix of forms. And we can assume that the first column has degree D1, and the second column has degree D2, and where obviously the sum of D1 and D2 has to be D, which is the degree of the curve. Okay? And so you have a resolution, the polynomial ring in free variable, the polynomial ring R in two variable, a free copy of it is mapping on I, and phi is our presenting matrix. And I always assume that D1 is less than equal than D2, okay, throughout the talk. Now, so this approach, why is this approach? Why do we use these pathways? Why don't we use the implicit equation of the curve? But first of all, linear relations are easier than polynomial relations. So this phi is easier to handle. Second of all, it's easily available to us, immediately given. And also, phi is the first step actually to compute the implicit equation, and usually it carries a greater deal of information. Also, this is not a new way. Applied mathematicians have done this, for quite some time to approach this problem from phi. Now, the way that the vessel that really connects the study of the singularity of the curve to this syzygy matrix is the Riesz algebra. So we are looking at the Riesz algebra of the ideal I, the ideal generated by F1, F2, F3, the ideal of the parametrization. So is the algebra generated by F1t, F2t, F3t inside the polynomial ring in one variable in T. And we can map the polynomial ring in 5 variables, k, x, y, t1, t2, t3, we call it B, into the Riesz algebra. The Ti will be mapped to Fit. And what we are looking for the kernel of this epimorphism. We are looking for J. This ideal J is called also the defining ideal of the Riesz ring. And looking or computing the defining ideal of the Riesz ring is a classical fundamental problem in elimination theory. And this problem has occupied commutative algebraists now, as we heard from Bern, for over 30 years, and also algebraic geometer, and more recently, even applied mathematician in geometric modeling and computer-aided design. It's not an easy problem to solve, but it's very important because Riesz algebra are like the prezzemolo, the parsley we say in Italian. They are ubiquitous, you find them all over. They, obviously, they give us the coordinate ring of blow-ups, but they're also the way to control, the growth of powers of an ideal, and they're also the ambient space where integral dependence of modules and ideal take place. Also, if you look at the defining equation, they give us the implicit equation of a very important construction, like secant variety and tangent variety in general, of images of map between projected spaces. So let's see how this is a vessel. What does this tell us? But first of all, the Riesz ring is the coordinate ring of the graph of my map C. You remember the map that was giving me, whose image was the curve C. So let's call this graph gamma, okay? Gamma is inside P1 cross P2, and so we can think of B, and this inclusion of gamma in P1 cross P2 algebraically is nothing else than that projection of B into the Riesz ring, of the projection of B onto the Riesz ring. So we can think of B as kxy, which is our P1, and cross kt1, t2, t3, which is our P2, okay? And then we have even a natural bigrading. Xy is graded by, with degree 1, 0, and the variable t1, t2, t3 are graded with degree 0, 1. This gives a bigrading, the bigrading goes directly to the Riesz ring, and J is a bihomogeneous ideal, and often we play with this bigrading. Aaron has done this forever, playing the grading of the XY against the T1, T2, T3, or consider the collect grading and stuff like this. And this will be very, very useful to us. Now, now, as I said, so gamma is contained in P1, P2, and we can project in the second component. And if we project onto the second component, we project the graph of C into the curve, we get, algebraically, the inclusion of the coordinate ring of the curve inside the Riesz ring. So we see that the coordinate ring of the curve is nothing else than the direct summand of the Riesz ring. So the Riesz ring definitely encodes all the information on the curve. And as usual, if you want to study the image of a map, the graph of the map will have much more information because it will encode all the information about the image. It will reveal much more, actually. So as we see, as I said, the Riesz ring contains as the direct summand the coordinate ring of the curve. And in fact, we can see it immediately just putting the xy degree 0 and letting the t degrees vary. But it also contains the idea of parametrization as a direct summand. We just can fix the t degree 1 and let the xy degree varies. Not only the implicit equation of the curve is encoded here. It's just a component of J again. We just can take the xy degree 0 from J and we get the implicit equation of the curve. But also the syzygy matrix is encoded here because we just take the component of J fixing degree T's 1. And we get, so everything is in this picture. So obviously this is a vessel. Okay, so now we want to talk about the defining equation. So when is this known? This is work with Andy Castin and Bernd Ulrich, and it's been spanning for a long, long time. So I talked about this, part of this, in Olinda already. We know this if D1 is equal 1. So if our syzygy matrix, the first column is linear. And this was actually work started by Aron, Vollmer, and Jo Young Hong, and then continued by Cox, Hoffman, Wang. And then we did it actually in more generality for any curve containing Pn. But we assume that the presentation matrix is almost linear, which means all linear except for one column at most. And then recently I did work with Kahneman Lane, taking this kind of ideal and extending it to many variables. And another case, what we know, is when D1 is equal 2. So the first column, and I talked about that case in Olinda, so I'm not talking about it here. The first column of the matrix instead is degree 2. And the third case we know is when D1 is equal to 2. So the matrix is so-called balanced. So the degree of the 2 column is the same, which is the most general case. Now, the method to solve this are completely different. For example, in the first case, you need to see, the way we did it is that we see the Riesz ring as a divisor over a normal domain that we know completely. We know very well what it is, and then we can compute the class divisor class group, and we can identify the equation of we can compute it explicitly and identify the equation of the Riesz ring with exactly an element of the divisor class group, and make this isomorphism explicit. Now, this tells us already that in the case of the Riesz ring of a sextic, we know everything. Because in a sextic, you can have, so sextic is degree 6, so D1 plus D2 is 6, so you can have 1, 5, 2, 4, or 3, 3. So everything is known. And our idea is to actually make a connection, and this actually started at Olinda, the idea started at Olinda, is making a connection between the Riesz algebra and the singularity of the curve. We want a correspondence. We believe that the correspondence existed, and we wanted to make the correspondence explicit. And we did this for sextic. I'm going to show you what we are after in the next chart. So the first column represents the matrix phi and the degree D1, D2. And the second column represents the Riesz algebra, more precisely represent the generator by degrees of the ideal J. Okay, so these are the generator by degrees of the ideal J, of our ideal we are seeking for. And the third column is the singularity of the curve singularity. Be careful, when I write the generators by degree of J, I omit always the one of the implicit equation of the curve, because it's always there, 0, 6. And I also omit the equation of the symmetric algebra, the equation, because they're always there. We know exactly what they are. They come from the syzygy matrix directly, and they are degree 1, 1, and 5, 1. Then, and so we see there is only one kind in with this rough classification of Riesz algebra for 1, 5, when D1 is equal 1. When D1 is equal 2, there are two kinds, and that depends whether the first column of the matrix has a generalized 0 or it doesn't, okay? Or if you want, if the first column generates a complete intersection or it doesn't. And in this case, the second case is more general and corresponds to the 10 double points. And then in the case 3, we have 3 kinds of Riesz algebra. Again, this classification is rough. It just means in terms of the generator by degrees of J. 4 kinds of Riesz algebra. Sorry?
What are you calling a double point? Is it cos of a double point?
Two means two generators of degree 1 and 3.
Sorry? Which question?
Is it cos of a double point?
No, here I mean nodes. 10 double points, I mean 10 nodes. So, multiplicity 2. 2, I mean multiplicity 2. Yeah, multiplicity 2. This just means multiplicity 2. Yeah. And these also include not just the singularity on the curve, but the infinite linear points, okay? So includes the singularity and the infinite linear points, which are the one you get by doing quadratic transforms. Includes everything. So in one you have 1 multiplicity 5, here you have 1 multiplicity 4 plus double points, and they can be also infinitely linear. Here you have 10 double points, and so on. And notice that the 4 cases here are distinguished, this is the most general, and they are distinguished depending how many points of multiplicity 3 there are on the curve. Okay? And I mean also infinitely linear, counting also infinitely linear. So if you have 3, this is the most particular one. If you have 2, you get this. If you get 1, you get this. And if you have if there are none, so 10 double points, you get this. And this is the most general condition. You see here that these 2, geometrically, there seems not to be distinction. And one could ask, what's the geometric difference between these 2? The Riesz algebra are obviously different. Okay? Here you are having 10 nodes so you don't know how to distinguish, and this is an open question. Because this, if you look at the parameter space in this case, this is an open set, okay? While this is in the boundary of it, okay? And so let's go on, and I'll come back to this chart later. We'll talk about it later. So now let's talk about the defining equation of the Riesz ring. So the usual way to study the equation of to study the Riesz algebra is by mapping the symmetric algebra onto it. Because as Bern pointed out, we know everything about the symmetric algebra, and we know very well what the equations are just coming from the syzygy matrix. And in this case, the symmetric algebra is very beautiful. It's a complete intersection defined by G1, G2. You obtain G1, G2 just multiplying the vector T1, T2, T2, T0, T1, T2 by the matrix phi. And the by degree of G1, G2 are the 1, 1, and the 2, 1. Clearly, the symmetric algebra gets the by degree from B, like the Riesz algebra does. Now, the Riesz algebra, this pointer. The Riesz algebra is obtained just from the symmetric algebra modding out a torsion, and so we can immediately see that the symmetric algebra, we want to compute this ideal A, obviously, and this will give us the Riesz algebra. And this ideal A, okay, is just obtained as the zero local cohomology of S. This S is the symmetric algebra, okay? Just because we obtained the Riesz algebra from the symmetric algebra modding out a torsion, okay? So now the beautiful thing is that if we want to compute, in this case, computing this zero local cohomology is quite easy because the symmetric algebra is a complete intersection, so we obtain it, we can resolve it using the Koszul complex. And then we can compute local cohomology along this resolution, and using the symmetry of the Koszul complex, one obtained this bigraded isomorphism, which was already known by Joannalou, but our method of proof is much, much easier. And there is a bigraded isomorphism, and here, this is a graded dual. It's the graded dual of S against T. S is the symmetric algebra. T, I remind you, is the polynomial ring K, T1, T2, T3. Okay? And this is quite useful. This is really the useful piece of information. We can, and this isomorph is even completely explicit by Morley formed by Joannalou. So it's made completely explicit. So this tells us immediately, this is actually even a perfect pairing, this tells us immediately that the best way to study A is via its bigraded components. So the corollary that you can see right away is I call this AI. This I means the degree in terms of xy. So I let the degree respect to the t varies, and I fix the degree respect to x and y. And this is isomorphous to the hom of S, and here I fix a slice, a graded slice of S. And again, this is the x degree, xy degrees, d minus 2 minus I, and the t degrees is left vary, against t. Okay? And because this AI is a hom, these are reflexive t module. So we get immediately this information. But we get much more, because this tells us, see, you can just take this by homogeneous resolution and you can slice it, you know. And then we can look at this module and look at this presentation. And it will be very nice. And obviously, this gives us immediately, then you can dualize it and compute this AI. So the numerics, obviously, of this presentation show us that the behavior of AI depends a lot where I sits in which interval. If you take I, for example, larger than d minus 2, then there will be no symmetric algebra in that degree, and then the AI will be 0. And if you take the I sitting in this last range, then the symmetric algebra will just be isomorphic to t in that degree, and then it will be free. And so obviously the I will be free as well. And also here there is an easier range, because only one of the two G1 that was the one of less degree, was the one of degree D1, will have taken place in the resolution, and the symmetric algebra will just be the co-kernel of the multiplication of G1 from T to T. And so it will be easier than this last first, if you want, range, where both equations take place. But even here, you have a resolution. You can use a resolution, but it will be more complicated. Okay, so what we see immediately from here are the rank, for example, of this AI. The rank of AI is, in the more complicated range, it grows up 1, 2, up to D1 minus 1, then it stays stable here, is always D1, and then it starts going down. And you can see the symmetry is given by the fact that the symmetric algebra is a complete intersection. Also, as I said already, the AI in this range are free, okay, and here they vanish. All right, so I already said they are free, and also, not only they are free, but what we can see right away, this is in the first range, I mean, if you want the last, the easy range, where the symmetric algebra is just free. There are no G1, G2 that came into play yet. And this ideal, the ideal the truncation of A in degree D2 minus 1 is just generated in degree D2 minus 1, 2, comma 2. In particular, this already tells us an information about the whole kernel we are looking for. This kernel will have xy degree at most, D2 minus 1. Not only, we know exactly what the generator are on the nose. We can compute them exactly. And the reason is because this ideal is given by linkage. So in this case, this is a perfect link of grade 2. In this case, because D1 is small, so G1, G2 is contained in M to the D1, you get a link, and so you know exactly what this ideal is. As I said, this was the easy range. We can describe everything. Now, the middle range. Already, this is more complicated. To be in the middle range, you need to have a D1 strictly less than D2, otherwise it's empty. And also, here you see already the relation with the singularity of the curve. If the T module, AI, we said always has the same rank, D1. And one could ask, is it free or not? But it's free if and only if the first column of phi has a generalized 0. And as I pointed out before, this corresponds to the fact that the curve C has a singularity of multiplicity D2, which is the maximal singularity it can have, multiplicity, the maximal multiplicity singularity can have on the curve. And in this case, AI is generated in at most 2 degrees. It could be generated just in 1 degree or in 2, and if it's generated in 2, they have to be consecutive. But we still don't know, we know how many there are obviously, but we don't know which one are the generator. We don't have them in the nose yet. And also, we don't know much if this is not happening, if there is not a generalized zero. The first range is even harder to describe. We can describe it if d1 is equal to 2. Clearly, we can always describe the case I equals 0 because that's just the implicit equation of the curve. This is classical. It's just a resultant. But then there is not much more we can say, unfortunately. We can compute it if d1 is equal to 2. In particular, for example, we know that this module is string of rank d1 minus 1 if and only of, again, a connection with the singularity, if and only if there are at least 2 singularities of multiplicity d2 on or infinite linear C. All right. So this is about the singularity and about the reasoning, and now I would like to pass to the singularity of the curve. And this is joint work with Cox, Cassin, and Ulrich, and as I said, it started in Olinda. I presented the work on the sextech, and then Cox asked, and we start working on the relation with the singularity of the curve, and now it's going to appear in the memoir of AMS. So let me start. As before, we have the same setting as before. We take a rational curve of degree D. It's parameterized by my form, F1, F2, F3. And we have degree D, and we are in the polynomial ring KXY. We have, again, our matrix of relation, because I said I'll use my matrix of relation. Same setting, the degree D1 first column, degree D2 second column. They're all forms, so everything the same. D1 plus D2 is D, the degree of the curve. OK, so let's go on. So this kind of investigation started from work of Eisenbach and Ulrich. Okay? So the way we investigate the singularity of the curve through the syzygy matrix, we consider P a point on the curve. And we think of P as a row vector. And we can multiply P by our matrix phi. And if we do that, we get 2 forms, okay? A and B, because our matrix phi, remember, had 2 columns, one of degree D1 and one of degree D2. And we call this a they call this a generalized row of phi. And the reason why they call it a generalized row of phi is because it's just a linear combination of the row of phi, where the combinator comes from P, from the coefficient of P. I mean, from the entries of P. And so this, what it turns out is that the fiber over P, so in the parameter space, the parameters that correspond to our point P in the curve, are defined by the ideal generated by A and B. So the ideal generated by this generalized row, by the entries of this generalized row. So this tells us in particular that we can count the number of parameters that correspond to our point P just studying this ideal. But because we started with a point on the curve, obviously, there were points in the parameter space that correspond to our P, and so means that this ideal, this scheme is non-empty, which means that this ideal has to be defined, the scheme has to be defined just by one single polynomial, which means that this A, B have to have a non-trivial GCD. Okay? And so the scheme is just defined by the GCD of A and B. And A and B, remember, are 2 forms of degree D1 and D2. So this tells us immediately, as I already said, and this was observed by Eisenbach and Ulrich, that P is in the curve if and only if the codimension of the ideal is 1. So you have a non-trivial GCD. And in this case, the number of counted with multiplicity, because this is a scheme, the number of parameters that correspond to our point P is exactly the degree of this GCD. And this is the multiplicity of the point, or if you want, is the multiplicity of the local ring of the curve localized at P. Also, you can learn much more just taking this GCD, member case algebraically closed, and writing it as a product of linear forms, okay, of linear independent forms. And then what do you get? You get that LLI correspond to the branches through P, and CI correspond to the multiplicity of the branches. So you get an enormous amount of information just by the presentation matrix, because remember, this AB was just a generalized row of my presentation matrix. And we call this the General Lemma, because this is a generalized row. And, but obviously the drawback is that you have to know the point. You have to start with the point, P. So the immediate consequence that the general lemma gives us is that if you take a point in the curve, the multiplicity of the point can only be either less than equal than d1, because it's the GCD of two form of degree d1 in the 2, or is exactly the 2. And this was already observed by Ashensi, which was a student of Eisenman many years ago, and now she's a doctor, and by Chen, Goldman, and Song, with, they are applied mathematicians with completely different method. And then also, we can do the same work if we take the curve, we take a point, a singular point on the curve, and we blow it up, and we look at the chart, and we look at the Hilbert-Birch of that chart. We apply the general lemma there, and then we can, investigate the blow-ups, and we can say the same kind of information, lots of information about the points on the blow-up. And then we can say that if Q is infinitely near C, then the multiplicity of Q has to be less than equal than D1 always. And I suppose this the geometry knew, but this is our way to do it. Okay, so, and this gives us a lot of information already, but we need even more. So now I'm going to look at the case in which is the most general case, in which the I just want to see how much time I have. I have 15 minutes, so it's good. In which the 1 equal the 2 is equal C, in which the Hilbert-Birch matrix is balanced. And in this case, okay, obviously by the general lemma, by what I said before, the multiplicity of the point on the curve or infinitely linear is always less than equal than C. And we are interested, we'll focus on the singularity having maximal multiplicity C. Okay, that's the singularity we'll focus on. And if you just use Max Noether formula on the genus, you know that there are at most 3 of such singularity, and so there are exactly 7 configurations of multiplicity C singularity. And when I say 7, I always focus, remember, on the singularity, on having multiplicity C. So you could have none, and that's represented with the empty space or with this tratto. You could have 1, on the curve, obviously, and this is represented by this C, or by a point. Or you can have C, comma C, and this means that you have 2 points of multiplicity C on the curve. Or you could have 3 points of multiplicity C on the curve. Or you could have a point of multiplicity C on the curve, and then 1 in the first quadratic transform. And then it's represented with this column here. Or you could have 2 points of multiplicity C on the curve, P1 and P2. And over P1 on the quadratic transform, you have another one. And then it's represented with C colon C comma C. Or you could have, you see, this is P1, this is the one over in the blow up, and this is the other in the curve. Or you could have 3 points of multiplicity C, but only 1 in the curve, our P, then you blow it up, you find another one, and then you blow it up again, you find another one. Okay? So these are the only possible configuration. And now I want to see how to differentiate this configuration using the Hilbert-Birch matrix. How can I read this from the Hilbert-Birch matrix? So I do this classification and even a stratification later using these configurations. So this is very important. I want to study and think about the singular point of multiplicity C. When do I got such point of multiplicity C? But I said you can read the multiplicity from the Hilbert-Birch matrix. So you have to take this P, you have to multiply it by phi, and then you get this A and B, this generalized row. And say that P has multiplicity C means exactly that the degree of the GCD of A and B is C. But A and B are 2 forms of degree C. How can their GCD have the same degree as the form? It means that the forms are linearly dependent, are one of the multiple of each other. And so it means that you can just find a vector V in P1 such that P times phi times the transport of V is equal 0 for some V in P1. And we call this a generalized 0 because it just means that you apply row and column operation and you create a 0 in the matrix. Okay? And this is very important for us. This equation is very important. That's how we go on. So I want to show how you read this from the Hilbert-Birch matrices. So this chart will show the correspondence. So the first column gives us the configuration of singularity. The second column gives me the Hilbert-Birch matrices. So if there is none, you can have these cases. This, for the sextic, you can only have this, because in the sextic, this Q1, the QIs are all linearly independent, and they are form of degree C. And in the sextic, these are form of degree 3, and there are only 4 linearly independent at most, so you only have this matrix. But in general, from degree 8 on, you can have all of them. And then if there is only one point of multiplicity C, we can always move the curve in such a way the point of multiplicity C is 0, 0, 1. And that means that we have this generalized 0 here in the last row of the matrix.
What is the meaning of the subscripts on the Q's?
This means that they are linearly independent. They are linear independent form. Q1, Q2, Q3, Q5, they're all linear independent form of degree C. That's it. So they are all distant, okay? And if you have 2 of them, 2 points, I can put one at 1, 0, 0, and one at 0, 0, 1. And that the 1, 0, 0 will correspond to this 0, and the 0, 0, 1 will correspond to this 0. If you have 3, then you can, obviously they cannot be on in the same line, they cannot be in the line, so I can put one at 1, 0, 0, one at 0, 1, 0, and one at 1, 0, 0, 1, and then you get the free GCD from here. And so on. The fact, when you have it in the blow-up, you read it from here from the fact that there is this repetition Q2 equal Q2. So, but anyway, the point of this chart is to show you that you can completely classify the Hilbert-Birch matrices, and they read completely. If you are in a standard form, they tell you immediately the configuration of multiplicity C singularity. The problem is, you know, this is the drawback both of this classification of the Hilbert-Birch and of the General Lemma. They don't give to us the singularity. You know, if you use Macaulay, you just get a phi. You don't get a phi in normal form. So how do you know from the phi you get from Macaulay which, you know, what's the normal form? So how can you read immediately the configuration of singularity? How can you locate this singularity directly? Okay? So to do this, we have to go back to our equation, the equation that tells us when do you get a point of multiplicity C. You have to have P times phi times Vt equals 0, where P is in P2 and V is in P1. So we consider this subset of P2 cross P1, and actually we think of it as a scheme, and we project it in the first component, and we get the scheme Z1, or we project it in the second component, and we get the scheme Z2. And the scheme Z1 corresponds exactly to the point in the curve that have multiplicity on or infinitely linear that have multiplicity C, and is defined by the 2 by 2 minor of a matrix C. And the scheme Z1, the scheme Z2, it's an auxiliary scheme. So this is the scheme we really want. And this is an auxiliary scheme, which is very useful because it's a scheme in P1. A scheme in P1 are very nice. And is also defined by a matrix, which we call A. How do we get this matrix C and this matrix A? I mean, by the 3 by 3 minor of this matrix A. How do we get these matrices? We get it from this equation again. Remember that, so C is a linear matrix, so a very nice matrix, with entering some variable Ti. A is a linear matrix in U1 and U2. And so they are defined by this equation. You take in the place of P, T1, T2, T3, free variable, because it's a point in P2. In the place of V, U1, U2, because it's a point in P1. And you have now a polynomial, homogeneous, in the variable T's, in the variable U, and the entries of phi were in X and Y form of degree C. So they will be this form. And so we can extract all the monomial of degree C in X and Y. And if we extract all the monomial in X and Y of degree C, and then we extract also the variable U1, U2, you get the matrix C. So it's linear in the T's. And if you extract instead the T's, you get a matrix which is linear in UI. Okay? And so this matrix C defines this scheme, the 2 by 2 minor defines this scheme, which is the scheme of interest. And the matrix A, instead, the 3 by 3 minor defines the scheme Z2, which is the auxiliary scheme. Why is this useful? Because we can prove that this is an isomorphism and this is an isomorphism. So in particular, these two are isomorphic, but that tells you that you can study your scheme of interest through a scheme which is very easy because it's scheme in P1. And so if it's non-empty, it's just defined by a single polynomial. And this single polynomial would just be the GCD of the generator of this ideal of minor. And so you can just take this GCD again, we can factor it out and study all the singularity from there. And indeed, we take the GCD of, a GCD of the generator of this ideal, we factor it, and the lambda I are linear forms, and the lambda I correspond through this isomorphism, this triangle I did before, to the point of multiplicity C on the curve. And not only the Fi, the exponent, give us the number of points that are infinitely near. In fact, Fi minus 1 is exactly the multiplicity of the local ring of Z1, the scheme of interest, localized at P minus 1. And is exactly all the points that are infinitely near P, which have multiplicity C. And this is much harder to prove. This just needs isomorphism. This needs the Hilbert-Birch matrix and the classification to be done. And then in particular, what you can see right away is that all the number of points of multiplicity P, C, either on the curve or infinitely near, are just given by the degree of Z1. Z1 is a scheme. And so they are just given by this ideal of the multiplicity of this ring, of this coordinate ring defined by the ideal of minor of C. And this is obviously also given by the auxiliary scheme, whose degree is obviously, because defined by this polynomial, this degree is just the sum of the phi's, but this is also can be expressed as 6 minus the minimal number of generator of I2 of C. And this fact is actually very interesting because this invariant was the invariant that we used many years before, 4 or 5 years before, 4 years before, to distinguish between the sextic, the algebra of the sextics when the 1 equal the 2 was free. We had 4 cases of sextics, 4 cases of different by degrees of the generator of J. Of generator of J, and the way we distinguish was through this invariant. In fact, if you remember, I told you back then, when we got to that slide, that there were 4 cases. They corresponded having free singularity of multiplicity C on or infinitely linear curve, 2, 1, or 0. And that's given by this number. Okay, so now we want to talk about how do we stratify the, do I have any time? Maybe not, sorry. I have to check, because I may not have any. I have 4 minutes. Yeah, I have 4 minutes, according to my counter. Okay, so I can say something about this. So we want to stratify the parameter space. So we start from the parameter F1, F2, F3. These are form, as I said, of degree D. So the parameter space just defines space 3D plus 1. But we don't want every parameterization. We just want the true parameterization. I call it TD, the one for which our map, whose image is the curve, is birational and base point free. And not only, I want to investigate, as I said, this configuration of singularity of multiplicity C, so I only want to look at the parameterization whose Hilbert-Birch matrix will have D1 equal D2 equal C. Okay? So, and this I call it BD. And we can prove that TD is open and also BD is open in in the whole space. And this stratification of BD is as following. So what does this picture mean? This is the set of all parameterization that, that yields curve whose multiplicity C configuration multiplicity C singularity is C colon C colon C, which means there is one in the blow up, there is one on the curve, you blow it up, you get one, you blow it up, you get one. And this is closed, irreducible and closed, and its dimension is 3C plus 7. Then, if you look at this, the disjoint union, these are all disjoint, the disjoint union of these two is also closed, and this guy is, so you take these two together, and the disjoint union is closed, and this guy is open on the union. And also is irreducible, and this is its dimension, and so on. So if you want to go to this one, for example, you take the union of this the one before him with him, and is all closed okay? And he is open on the disjoint union. And is irreducible, and this is his dimension, and so on. So this gives this stratification into reducible locally closed set. And the way we do it to compute the dimension, we use the Hilbert-Birch matrix. To prove irreducibility, we also use the classification of Hilbert-Birch matrix. To prove this closeness and openness, instead we use the Biprouge lemma, that one. Okay, so this is just says what I said before, that the BD is the disjoint union of the sets, that each set is irreducible, and then that the closure of each set is obtained by the previous one that formed the boundary. Okay. Our work here, that's a big problem, and a big ingredient, actually, which was very difficult to get, is that our work is through phi, always, I said, through this Hilbert-Birch matrix. But we need to stratify the space of parameterization. So we need to pass from the parameter to phi. And we prove that indeed exists a generic CZG matrix, which you can obtain if you look at whose entries of this generic CZG matrix are exactly forms in X and Y, whose coefficient come from the coefficient of F1, F2, F3. Okay? So you introduce this new variable Zij, which are the coefficient of this F1, F2, F3, and you can write phi respect to them. And that's how you show that BD is open and so on. And I think I'm finishing up here. Thank you very much.